Okay, so let's start with our topic, impedance. So for impedance, or Z, it is the ratio of phasor voltage V to the phasor current I in ohms. Its unit is in ohms, so you can compare it to the DC equivalent. So in DC circuits, we call it as the resistance. In AC circuits, if we're going to translate it, we call it impedance. So we can just use that analogy. Okay, for rectangular form, so we have Z, or the impedance, equal to the resistance plus reactance. So the resistance is in real numbers, so this is the real part, while the reactance, it is the imaginary part. If we want to express it in polar form, we can do so. So this is the equivalent polar form. So the magnitude Z bar angle. So this one, this one is our x-axis, our resistance, while our y-axis is the reactance, and the resulting vector is the impedance. This one is the angle, theta. So we can use Pythagorean theorem to solve for z and also the angle, theta. So we have r squared plus x squared is equal to z squared. So just like a squared plus b squared equal to c squared. So for us to get the resulting impedance Z, we have square root of r squared, resistance squared, plus the reactance squared, or x squared. For the angle, we have theta equal to arctan of reactance over resistance. So where is our arctangent? So opposite side over adjacent side. So x over r. So tangent. Okay. The angle, we can express it in degrees or radians. So be careful in using degrees or radians. You will know if it's in degrees because you will see a degree sign or symbol. Then if there's no degree symbol, it's in radians. Here are the elements. Here are our elements that we're going to use. We have resistor, capacitor, and inductor. For impedance of resistor, we have R. So we don't have any imaginary component. So Z is just equal to R. For capacitor, we have 1 over J omega C. And for inductor, we have J omega L. Okay. You already know the symbols for resistor, capacitor, and inductor. So this is the symbol. I got this from LT Spice, so that you can imagine it the same way. In the same way, you're going to see it in your simulation software. Okay. Okay, for the legend, remember omega is the angular frequency, and the angular frequency is equal to 2 pi f. So what is this f? F is the frequency. Oop, what is it, Chugi? Omega is not, oh, it is, okay. It is angular frequency. Just a reminder, omega is angular frequency. Okay, let's proceed with phasor diagrams. Okay, na-distract ako kay Chucky. So we have our AC circuit with a resistor. So this schematic diagram only involves resistor. So later, let's express or illustrate the current and voltage in terms of phasor diagram. We have 100 bar 0 degrees as our AC signal, and we have 5 ohms. So how do we solve for current? So current is still voltage over impedance. Voltage 100 bar 0 degrees over 5, since there's no imaginary part, so the angle will be 0. Or you can check if you want. 5 bar, 0 degrees. So it's just 100 divided by 5, so 20. 0 degrees minus 0 degrees, 0 degrees. So our phasor diagram will look like this. So this is our current I, 20 daw yon in terms of magnitude, while our voltage V is 100 volts. So, 100, and also in 0 degrees. Okay, so next, let's see how will it look like if there is only an inductor in the AC circuit. So previously, all voltage, resistance, and current, they are all in 0 degrees. So if it's a resistive circuit, so voltage and current are in phase. Let's see how about if there is an inductor. So again, we have 100 volts, 100 bar 0 degrees, and we have J5 for our reactance here in our inductor. So let's solve for the current. The current is just 100 bar 0 degrees over J5. Let's remove this J5. Okay, so let's proceed with the analysis of the current and voltage if we only have inductor. So let's see. So here we have I equal to 100 bar 0 degrees over J5. So let's express J5 also in polar form. So we have 100 bar 0 degrees divided by 5 bar 90 degrees. Okay, so you can convert it using your calculator, this one. Just type in 5I in complex mode and then change it into polar form because this one is in rectangular form. Okay, so our current is 100 divided by 5, so 20. And for the angle, we have 0 minus 90 degrees. So we have 20 bar negative 90 degrees. If we're going to draw it in phasor diagram, so this is how it will look like. So we have the current I, we have the voltage V. So they are 90 degrees apart. Okay. Current is 20 in magnitude. So we can assume this is 1/5 of 100. And they are, so 20, negative 90 degrees. So this is the 0 degree reference. This is negative 90 degrees. Okay. So remember LE. LE voltage is E, L inductor, I current. So current is lagging in what? An inductive circuit. Okay, so as you can see, if we are going to rotate this in counterclockwise direction, the voltage V will be the first one to rotate, right? Oh, delayed to eh. Ito muna. Okay, so LE. Voltage yung magli-lead bago yung current. Okay, next one is what if, or how will our phasor diagram look like if we have a capacitor in our AC circuit? So we have 100 bar 0 degrees again. This time we have negative J5 for the capacitance. I mean, the reactance of the capacitor. Okay, this is not the capacitance, this is the reactance. The equivalent reactance. Because if it's in capacitance, it will be expressed in farads. So I is equal to 100 bar 0 degrees. Still, we have 0 degrees. 100 bar 0 degrees divided by negative J5. The impedance is negative J5. So, express this in polar form. We have 100 divided by 5 and then 0 minus negative 90 degrees. So, we have 20 bar 90 degrees. Okay. So, this is how it looks like in phasor diagram. This is the current I, this is the voltage V. So, they are 90 degrees apart. And for a capacitive circuit, remember ICE. So I is leading than the voltage, or the current is leading than the voltage in a capacitive circuit. So if we're going to rotate this in a counterclockwise direction, counterclockwise, so we have current mauna before yung voltage. Okay? So what if we combine R, L, and C, resistor, inductor, and capacitor in a single circuit, in a series circuit? So still we have 100 bar 0 degrees as our voltage, AC source. Then we have 3 ohms as our resistance, J8 for our reactance inductor, and negative J4 reactance for the capacitor. So first, we don't know the impedance. So first, we need to solve for the impedance, Z. So Z is equal to 3 plus the imaginary parts. So you can solve for the impedance given these 3 ohms, J8, negative J4. So what you need to do is add all the resistances, all the real parts, then add the imaginary parts. So here we have 8 minus 4, 8 minus 4, J. So next, we have 3 plus J4. So that is our impedance in rectangular form. So next is Z equal to 5 bar 53.13 degrees. So this is the equivalent in polar form. We need to translate this in polar form because our voltage is in polar form. So in solving for current, we have 100 bar 0 degrees divided by 5 bar 53.13 degrees. So current is 20 bar negative 53.13 degrees. Okay. So as you can see, the angle for current is negative. Okay. That means this is inductive. Remember, in a purely inductive circuit, earlier we have negative 90 degrees for the angle of current. So here, since we have a capacitive component, it will just be between 0 and negative 90 degrees. Okay. So this is the phasor diagram for the series RLC circuit. So 100 bar 0 degrees voltage. So this is the current, 20 bar negative 53.13 degrees. Okay. So